Okay, since it is southern one random walk, starting point is the S500, as for example here. So when we run the algorithm, we need to generate the multiple episode trajectories. Okay, we need to generate trajectory from the S500. So this is the starting point. Based on the setting, we can generate, okay, can visit one of the 100 neighbor states, left or right. And if only when they reach to the, okay, only when they reach to the either leftmost or rightmost state, they can have a reward. So in this case, if they have this return GT1 equals 1, means that they already reached to the rightmost, right, which has 1 reward. And the leftmost is -1, rightmost is +1, right? So in this case, for the one hot encoding, the first one is X500. We use the one hot feature vector. So this S500 will be located in the 5th location of this weight. So that's why we give 1 to here, because this state is located in the 5th location. If you see the count 1, 2, 3, 4, 5, the 5th location of this vector. So we give 1. For the next state, assume that this trajectory from S500 jump to the S548. Now, actually, it will move to the vector will be moved to the 6th position. Okay, the 6th position. So which will be somewhere here. Okay, which is located in the group 6. Now you can continue to generate this one hot feature vector. For example, the next state is the S490. S490 will be S490 will be jump back to the group 5 somewhere here, right? If we consider that the 100 state, 490 close to the S500 somewhere here. So then it will be the same to the S500. The one hot encoding, the location will be here. This is how you can generate the sequence or trajectory for episode. So for each episode, you can generate this kind of sequence. One thing is that when we generate this trajectory or sequence or steps, actually we don't know how many steps it will have for a particular episode. Actually, it's random until it's reached to the terminal state. It can like jump 100 steps, then reach the terminal state. It may move 200, 300 steps, then to reach a terminal state. So the size of the trajectory is not fixed. It depends on the problem setting, right? Because it depends on the action probability, either move to the left or right. Okay, this is the update for the previous problem setting. Now, from the source code level, how you can implement, how you can understand. As I mentioned, this is the source code level, the gradient Monte Carlo process for the estimation, the state estimation. So you have a state, the initial state, and trajectory. So this trajectory list will save each state's state information. We initialize the reward as a 0. So now this while loop will generate the trajectory. Okay, so while state not in the end state. So end state is there are 2 states inside, either leftmost or rightmost, the two terminal state, right? So we get action. This get action function will generate either positive will move to the right, negative will move to the left. So you will have so we just use a number to represent either move forward or move backward, right? So this action. Now we put this action and the current state to this step. So this step will be following the current problem setting. So we generate a integer, random number integer from the step range. So the step range is 100. Since we are counting from 1, so 1 to 100, 101, okay? It will select a random number among this range. This integer will be times with this action, because this action will be either 1 or -1, the positive 1 or -1. So it will decide whether it move forward or backward, left or right, right? Move forward, it will positive, or backward, it will negative. Then we put this step to these states. The current states, if it's at the beginning, the state will be 500, then plus this step. If it's positive, it move forward. If negative, it move backward. Now the next step is we'll decide whether we are in the terminal state or not. If we are in the terminal, you just decide the this minimum operation to decide if we are in the rightmost the state, right? So it's the size of the state, and +1 means that we are reaching to the rightmost terminal state. Then we get the minimum one, because if this state is larger than the size of the state, it means that it's larger than the 1,000 state, means that it's already reached to the rightmost terminal state, right? Then we just get the minimum one, which is this the rightmost state, right? So if it hasn't reached to the rightmost, then we just check again to the maximum operation to see if it's reached to the leftmost state. Okay, then because that the leftmost states, the index number will be 0. So we just select the maximum one. If the maximum one is 0, means that it move out, become negative. This state side become negative. Then we just get the 0. So we just check this state, the terminal state, whether if it's the leftmost state, then we get the reward -1. If it's rightmost state, we get the reward 1. Otherwise, 0. It follows the problem setting, right? Only when you reach to the rightmost terminal state, you get 1, positive 1. If you reach to the leftmost state, you get the -1. Other movements will just have the 0 reward. So eventually, just return state and reward back to this gradient MC prediction. So we generate the new state and then this reward. With this action, we have a new state and reward. Then we put this state into this trajectory, then update the current state for the next state. Then we just generate until we reach to this state become an end state, either 0 or like 101, 1,001. Yeah, because the number of states will be the 1,000, 1,001. Okay. Then after that, we can do the gradient update process. If you remember how we did the gradient, we first calculate the error correction, delta equals alpha. Alpha is the time step size or learning rate step size. Alpha times the reward we got from this trajectory minus which will be ut, right? In the Monte Carlo method, ut minus its value function. So we just want to get the value of this state, the current value of a particular state. Initially, all the state value will be 0, but after a while it will be updated, right? So then just calculate this error, then times the step size, put the delta, and with this update process, so the value is just get the value of the state, and update is the actual we are updating the weight vector, right? The weight vector will be updated here. Then, yeah, so the remaining are just the distribution. We collect some statistic information about the states. Which state we visit very frequent, with which state we've less visited. Okay. this is from source code level, how you can understand this problem. And also here, when we do this value function update, actually in these updates will be the actual implementation. There could be multiple different kind of implementation. You can use the polynomial basis function. It can also be Fourier basis function. It can also be the higher coding that we learned in the last lecture or last lecture, right? There are multiple ways to do this update. Depends on how you define the weight, right? The state feature vector. Okay, this is what so I want to update for this state aggregation we learned, just to remove those confusion, okay, to make it more clear. Okay, so before we jump to new knowledge, so let's have a quiz. First.